Welcome back, everyone. In this second lesson on Chapter 3 on derivative rules, we're going to learn derivatives of exponential functions and cyclic or sinusoidal functions. So the first one we're going to talk about is the derivative of e to the x. It may be the simplest derivative rule there is. The derivative of e to the x is e to the x. So if you have an exponential base e, its derivative is e to the x, or itself. If you have a derivative of an exponential base b, where b is not equal to e, it is b to the x, so it repeats itself, but then you have to throw in this natural log of b factor in there. So let's take a look at an example using that. Unpaid credit card balance. It says if credit card purchases are not paid off by the due date on the credit card statement, finance charges are applied to the remaining unpaid balance. In July 2009, one major credit card company had a daily finance charge of 0.062% on unpaid balances. Assume that the unpaid balance is $2,000 and that no new purchases are made. For Part A, it says find an exponential function for the balance owed, future value, d days after the due date. So if you recall exponential functions, so f of d is equal to the initial value, so in this case 2,000, that's our a times b to the x. Our b is 1 plus 0.062, because it's a percent, divided by 100 to the d, and that's in dollars, and d is how many days. So that would simplify to 2,000 times 1.00062 to the d. So what we have there is we have an exponential function with a constant out in front of it. The base of that exponential function being 1.0062. In Part B, it says how much is owed after 30 days. So f of 30, if we plug that in, we get approximately, I'll leave that up to you to check, approximately $2,037.54. And you can verify that with your calculator. In Part C, it says write the derivative formula for the function in Part A. So now we start putting together multiple rules. So the constant 2,000 can come out. So f prime of x, or d, f prime of d is 2,000 times the derivative with respect to d. So d, a little confusing there, of 1.00062 to the d, which is 2,000 times 1.00062 to the d times the natural log of 1.00062, using our rule from above. That simplifies to approximately 1.24 times 1.00062 to the d. And then finally in Part D, it says how quickly is the balance changing after 30 days. So we're finding the rate of change at 30 days. So we plug that in, and we get 1.24 times 1.00062 to the 30th, and that turns out to be approximately $1.26. This is kind of redundant, but dollars per day. As a matter of fact, it's not redundant. I should not have that right there. So there's an example of using the derivative rule for exponential functions. The next thing we're going to do is we're going to talk about derivative rules for log functions. Similar to the exponential function, the derivative of the natural log function is 1 over x, and by similar I mean same base. And the derivative of any other log base is, we're going to use the change of base formula here, if you remember that from calculus. Log base b, or pre-calculus, log base b of x can be written as the natural log of x over the natural log of b, which can be written as 1 over the natural log of b, because that's a constant, times the derivative of the natural log of x. So that actually turns out to be 1 over ln of b times 1 over x, which sometimes is combined as 1 over x natural log b. So that's the derivative rule for any log function base b. So let's take a look at an example using that rule. A dieting website offers the following advice. After a few weeks of fast weight loss on your diet plan, you may experience a weight loss plateau effect. You are eating no more than usual, but you stop to lose weight fast. Why? Because your body has slowed down and is making calories go further, and you cease to lose weight fast. As a general guide, here are the optimum average rates of fast weight loss in the table. So based on body weight, the weight loss in pounds. So let's see what the questions are. The input is aligned to 10, 20, 50, and 90 pounds by subtracting 130 pounds from each body weight. Optimum weekly weight loss is modeled by the function P of W is equal to negative 1.875 plus 1.284 times the natural log of weight in pounds, where W plus 130 is the dieter's body weight. Data ranges from 10 to 90. A graph of P is shown in figure 3.22. Okay? Find a model for the rate of change in the optimum speed of weight loss. So what they're asking us to do is to find P prime of W, and P prime of W is going to be the derivative of P of W, and the derivative of the constant, negative 1.875, is 0. The derivative of the next part, the constant rule, is 1.284 times the derivative of the natural log, which is 1 over W, which turns out to be 1.284 over W, and the units would be pounds, which are the Y units, divided by pounds of body weight. I'm going to make that clearer. Pounds of body weight. They're both in pounds, but one's pounds of weight loss and the other one's pounds. Let's say that. Pounds of weight loss. The rate at which you are losing pounds based on your current body weight. That's part A. In part B, they are asking for the optimum weight loss, not the rate of change of optimum speed of weight loss. So they're asking for P of a person who weighs 200 pounds, but W, the input for that, is going to be equal to 200 minus 130, because they say they subtract 130 to create the scale they have for W. So that is P of 70, and P of 70 is going to be negative 1.875 plus 1.284 natural log of 70, and you can verify that. That turns out to be approximately 3.58 pounds. And then finally C, what is the rate of change in optimum weekly weight loss for a person with a body weight of 200 pounds? So in this case, they're asking for P prime of 70. So P prime of 70 is going to be 1.284 over 70, which turns out to be 0.018 pounds of weight loss per pound of body weight. That is the rate at which a 200-pound person would be losing weight. And for the last two derivatives that we're going to cover, we're going to find the derivative of the cosine and the sine function. So the top graph you have there is the cosine function, and we're going to come in and draw some tangent lines. So at the very left end, a slope of 0, negative slope, 0 slope, positive slope, 0 slope, negative slope, 0 slope, positive slope, 0 slope. And then we're going to go back and we're going to plot points to represent the value of those slopes. So 0, negative, 0, positive, 0, negative, 0, positive, 0. So at those x values, those are the values of the corresponding slopes, and then we're going to connect those points, and it turns out that the derivative of the cosine function is not exactly the sine function. It's the reflection of the sine function over the x-axis, so it's the negative sine of x. Why don't you pause the video and try and do the next one on your own. So we're going to approach this one the same way, the derivative of the sine function. So we're going to draw the slopes in, positive 0, negative 0, positive 0, negative 0, positive. So we start on the far left-hand side, positive, 0, negative, 0, positive, 0, negative, 0, positive. And then we connect the dots, and when we connect the dots, we see another sinusoidal function emerging, and the derivative of the sine function is actually the cosine function. The derivative of the sine is the cosine, but the derivative of the cosine is the opposite of the sine.